Okay, moving on to section 9.6, which deals with hydrohalogenation. So adding HBr or HCl across a double bond, something that we looked at in the alkenes chapter. We talked about how if you add or if you do a hydrohalogenation on an alkene, it proceeds with Markovnikov regioselectivity. Well, we see the same thing happening when we try a hydrohalogenation with an alkyne. We get Markovnikov addition. The rich are getting richer in hydrogens. Well, again, if we do it on a terminal alkyne, this carbon is the one that's richer in hydrogens. So it takes the extra hydrogen and the other carbon takes the halogen. So we have to still know Markovnikov regioselectivity. One thing I would point out, though, is that when you're doing hydrohalogenation on an alkyne, I like to specify that I'm using one equivalent of my hydrogen halide. Because if you use more than one equivalent, then you just keep adding, right? You're going to take the alkene and it's going to react as well. So you actually end up with a geminal dihalide in that case, right? So the rich is getting 2 times richer, I guess you could say, right? This carbon that has the hydrogen attached to it, now it's getting 2 more hydrogens, right? So it's getting doubly rich, I guess, when we do that double Markovnikov addition, okay? Kind of is how you would frame that maybe. So you don't need to know the mechanism of the formation of the geminal dihalide here. You don't have to know that because the mechanism is termolecular. That's all I really put in my slides about it. So I'm just going to leave it there. You guys have enough to memorize at this point. So I'll leave that as more of an FYI thing if you want to look into that. But with respect to anti-Markovnikov addition of HBr across the double bond, well, we saw that we could do that in chapter 8, but we can also do it with a triple bond. It says here that peroxides can be used in the hydrohalogenation with HBr of alkynes to promote anti-Markovnikov addition, just like we saw with alkenes. But just like we also saw with alkenes, you can only use HBr to do this. So again, this is anti-Markovnikov addition, and you end up with a mixture of Z and E isomers. Okay, you always end up with a mixture in this case. But again, you can do an anti-Markovnikov addition on an alkyne. So what have we got then? We can do a double halogenation on an alkyne, right? This is like our double Markovnikov addition. But we also saw in an earlier section, in section 9.4, we saw that we can take a geminal dihalide and we can do a double elimination followed by addition of water to make a terminal alkyne. And so the hydrohalogenation of an alkyne and the elimination of the dihalide to form an alkyne, they represent complementary reactions, and you need to know these reactions, okay? So with that in mind, let's take a look at a problem here. A couple of problems. It says, predict the major products expected for each of the following reactions. So we're starting it with a geminal dihalide. It's the same one in both reactions, but in the first 2 steps, we're doing the double elimination followed by deprotonation, then addition of water to form the terminal alkyne. So after the first 2 steps, you'll end up with this terminal alkyne. Be sure to draw the molecular geometry properly, right? We've got 2 carbons, right? So that means we've got 1, 2 carbons like this. So you end up with this molecule. Then what are we doing in the next step? We're treating it with HBr and peroxides. So this is going to do an anti-Markovnikov addition of HBr across that triple bond. So we're going to end up with a mixture of E and Z isomers. So we'll end up with this, which is the E isomer, and then we're also going to end up with some of the Z isomers. So we'll be sure to draw that as well. There we go. So we get a mixture of E and Z, or you could call these cis and trans as well. The next one, the first 2 steps are the exact same, right? We do the double elimination, then the deprotonation, followed by addition of water to make the terminal alkyne. So let's pencil that in. We have our terminal alkyne. And then in the next step, you're doing a hydrohalogenation just with excess HBr. So excess means more than 2 equivalents. Okay, it's essentially what it's saying. So you're going to end up doing one addition, right? And then a second addition to give you this compound. So it's like a double Markovnikov addition of HBr across the double bond, like that. Give me a thumbs up if you follow me on that. It's kind of a matter of memorization. Again, this is the mechanism that's termolecular mechanism, okay? So basically, in terms of the rate law, the rate is equal to the rate constant multiplied by the concentration of the substrate multiplied by the concentration of HX squared. And again, I'm never going to ask you about that. I don't think I've ever asked it on a quiz or anything before, so I don't think I'm going to start now. The only reason I'm bringing it up is that he does talk about it extensively in the book, and I think the point is this: is that you see a reaction like this, you say, well, it's just a double Markovnikov addition. Let me show you what the problem is. Let me go over to a blank document here. I didn't plan on doing this, but let's just go over it here. The problem is this, and again, I'm not going to go into too much detail, but if you do the first addition, okay, when you have the triple bond, okay, if you treat this with HBr, let's say, okay, you draw the curved arrow for the protonation, which there's nothing wrong with that curved arrow, you end up with this. So you would end up with your proton over there, but you'd end up with a cation like this. This is a vinylic carbocation, vinylic carbocation, which is very unstable. So unstable. It's about as stable as a primary carbocation. And so this is going to be avoided at all costs. And that's why a termolecular mechanism has been proposed. And again, it goes into some detail about it in our textbook. It goes into a little detail about how the mechanism is more like where you would have your 2R groups. I'll just show you an abridged version of it here, maybe, where you have the 2R groups. You have one molecule of HBr here, and then you have another molecule of HBr, and you kind of have, you know, one proton being added like this, okay? And then you have the other proton coming in like this. So you get both protons kind of added at the same time, and you end up with a transition state where you have a partial positive charge on this carbon, which is better than having a full-on positive charge on a vinylic carbon. And again, since we have the substrate and 2 molecules of HBr, that shows you that the rate law is the rate is equal to the rate constant multiplied by the concentration of the alkyne multiplied by, in this case, it would be HBr squared. So it's a termolecular mechanism, right? It depends on its first order here and second order, right? So overall termolecular means third order. Now, again, the reason I'm explaining all this to you is this, is that when you go into chapter 8, we looked at mechanism after mechanism after mechanism after mechanism in that chapter. What you're going to notice is that as we go through the next few sections, there's a couple of mechanisms that show up that are very important, but there's a bunch of mechanisms that you're kind of like, why aren't they writing a mechanism for this? Why is it left out? And the reason why is because some of them have these kind of termolecular mechanisms where, you know, you need to avoid forming these vinylic carbocations. I'm not saying they're beyond the scope of our class, but they're just left out because they're a little more complicated. So they might be just, you know, a little more complex or a little more involved. And so, you know, he kind of brushes over some of those things or skates over them, if you will. All right, so let's get back to the task at hand and find out. Well, let me find where we were. It was somewhere in here. So we'll go back down here, okay? And we just looked at that double Markovnikov addition, and I explained why you can't just draw, you know, one HBr being added by after another because you want to avoid that vinylic carbocation formation. All right, so let's talk about the hydration of an alkyne. All right, we looked at the hydration of an alkene, and I'm just going to do a little review here with you, right? We saw this, you know, Avogadro's number of times, where's my pen, where you could take an alkene like this and you just treated it with H3O plus, right? And what did you end up with? You ended up with Markovnikov addition of water across the double bond. So you added the proton here, rich got richer, and that was all good. Well, the thing is that we could draw a mechanism for this too, couldn't we? We drew a hydronium ion like this, and everybody knows that the first step is protonation, and then you end up forming an intermediate that looks like this. So you end up with this intermediate right here. Well, think about that based off of what I just told you. If you were to try to draw that same mechanism here, if you were to just draw a straight-on hydronium molecule to do the Markovnikov addition of water across an alkyne, you would end up with what? Okay, the rich are going to get richer. Let's draw that. You would end up with this. Uh-oh. You'd end up with a vinylic carbocation, right? Which again is highly unstable. So we can't just throw aqueous acid at an alkyne and get a Markovnikov addition of water. It's actually pretty sluggish without it, right? We want to compensate for the formation of that vinylic carbocation and the reaction being really slow. And so what we do is we add HgSO4 to the reaction mixture. So HgSO4, you can call that mercuric sulfate, or you can call it mercury 2 sulfate. Okay, so we actually throw mercury sulfate into the reaction mixture. Okay, and what that does is it enables the reaction to proceed. It's just basically spruces up the reaction so that it will work. So instead of putting aqueous acid, we always write water and sulfuric acid and mercuric sulfate. Okay, and what would that give us? Let's think about that. I mean, you don't get a regular alcohol. You get an alcohol that has a double bond on one of the carbons, okay? Or on the same carbon with the alcohol, you end up with a double bond. So this is called an enol, and that comes from alkene, right? You've got an alkene in the molecule, and you also have an alcohol in the molecule, so enol. But the enol is actually, in most cases, unstable, and it undergoes a process called tautomerization. So tautomerization, which is the migration of a proton and a double bond. So it's essentially an isomerization to give you a ketone. The reason why it forms the ketone is because the carbonyl is so much more stable. Okay, so it just spontaneously rearranges, and the process of that rearrangement is called a tautomerization, and you end up with a ketone. So there you go. So the mechanism of tautomerization is a mechanism that you have to know. Everybody needs to know how to draw this mechanism. So you start with the enol, you do a proton transfer, then you can draw these resonance structures, and then you do another proton transfer and you end up with the ketone. So what we say is that the enol, which is this, and the ketone, we say that they are tautomers of one another. And again, the definition of a tautomer is nothing more than isomers that differ in the placement of a hydrogen atom and a double bond, right? Look, I'll circle the double bond here in red. It went from here to here in the ketone. Also, you can see that this proton that I'm circling in green, okay, on the alcohol, it ends up on this carbon when we do the rearrangement, okay, or the tautomerization. So if you do an acid catalyzed hydration of an internal alkyne, well, that's going to give you a mixture, isn't it? Okay, there's no Markovnikov or anti-Markovnikov that you could do. So you're going to end up with a mixture 100% of the time. So you might think, well, that's not a very, useful reaction. And it depends on the situation. Okay, it depends. But again, there's no, right, think about it, since neither of the carbons has a hydrogen, there is no Markovnikov or anti-Markovnikov to consider. So let's take a look at this question here. It says 9.18 says, draw the major products that you would expect when the following alkyne is treated with aqueous acid. So that's aqueous sulfuric acid is what it should say, in the presence of mercuric sulfate, okay, or mercury 2 sulfate. Well, we know that this is going to be a Markovnikov addition of water. The rich get richer. So that means that this carbon is the one that's going to take on the extra hydrogen. And I'm going to end up with, I'm going to end up with this intermediate. But this is called an enol. And the enol is going to undergo tautomerization. So In our book, I think he always just draws the arrow in one direction like this to form a methyl ketone. And so we go from the enol to the methyl ketone. Methyl ketone. There you go. So Markovnikov addition of water across the triple bond does not just involve aqueous acid. It is not a simple mechanism that you can just draw the carbocation and walla walla bing bang. No, it is a reaction that is special in that it requires aqueous acid, yes, but it also requires mercury sulfate. To avoid the formation of a vinylic carbocation, you end up with an enol instead of an alcohol, and that enol undergoes tautomerization to produce a ketone. So instead of making an alcohol, you end up with a ketone. Well, let's take a look at another practice problem. This is the next one from the textbook. It says, identify the starting alkyne that you would use to prepare each of the following ketones via an acid catalyzed hydration. Well, the first thing I notice in A is that we have a methyl ketone, right? In terms of our retrosynthesis, that methyl ketone would come from this molecule. It would come from this enol, and that enol would come from this alkyne. So where we have this, and then we have the triple bond here. So this is the alkyne that we're going to have to start with. Right, we're going to start with that alkyne. Okay, we're going to start with this alkyne. Oops, there we go. Son of a gun, that's not very pretty. Can fix that up. So we'll start with this alkyne. We're going to treat it with what? We're going to treat it with aqueous acid, H2SO4 and water, and mercuric sulfate or mercury 2 sulfate. And that is going to give us the enol, this one here, which is going to undergo tautomerization. So tautomerization to give us the product. Now, I don't have enough room to do the next one. So I'm going to switch over to a blank document here just for a sec. So let's take a look here. And this is 9.19, and this is B. And it's this ketone, and this ketone is unsymmetrical. So here we go. So we have a couple of options here, right? It's not a methyl ketone, but we could either start with an alkyne where the triple bond is here, which would look like this. So you'd have one there and there. So 1, 2, 3, 4, 5. So you'd have this alkyne that I have here, or you could have the triple bond here. Okay, so that would be this, where you would have this alkyne. Could anybody tell me which one of these would be the best alkyne to start with? There's only one right answer. One of them, I didn't mean to do that. Would I want to start with the blue alkyne or the red alkyne? Absolutely, it's the blue one, right? The reason it's the blue one is because it's got symmetry down the molecule, okay? It doesn't matter where the oxygen adds, and it doesn't matter where the proton adds. If you do, after you treat it with sulfuric acid, water, and mercury 2 sulfate, right? It wouldn't matter which carbon you added to. It doesn't matter if you end up with this enol, like this, or if you end up with this enol, where you have this, okay? Because both of these, does everybody recognize the relationship between these two molecules? Can anybody tell me what the relationship between these two is? What's the relationship between these two molecules I have in the yellow circle? I'll give you a clue. It starts with I and ends with dentical. They're the exact same molecule, right? They're the same molecule. So they're both of these would undergo tautomerization, okay? They would both undergo tautomerization to give you this compound, okay? They're both going to give you the exact same compound. Whereas this one, the one that's in red, so sorry, I'm going to have to move it down here to make a little room for myself. Okay, but this one, you could either add the hydroxyl here. You could do that, or you could add it down here. This. Okay. So the one that's in black, that's going to undergo tautomerization to give you the right compound, okay, which is the right compound. But the one that's in blue, that's going to undergo tautomerization to give you this compound, right? And this is not the right compound, okay? This one's the right compound. So the answer is the blue alkyne is going to only give you the right product, whereas the red alkyne is going to give you a mixture, okay? And this, maybe I shouldn't have crossed it out, but we'll just write here, we'll write undesired, okay? Okay, so this one gives a mixture, okay? And then this one gives desired product only. Product only. Give me a thumbs up if you follow me on the rationale for what we're talking about here. Sorry, it's hard to squeeze it all in on the same page, but you can press pause here to see the whole dissection. Okay, cool. I think it's a good problem. I think it's a great problem. This is the kind of problem that they ask on, final exams and MCATs and that kind of stuff. Just seeing if you get your wits about you. It's not a moving a mountain kind of problem, but you have to understand what's going on, right? It's kind of like asking two questions in one, which is a big thing on standardized exams. All right. Yesterday I was in the lab at the university, and there was a student there studying for the MCAT. All right, where am I? Where are we? We're over here. And now we've finished this problem. We talked about the hydration of an alkyne, which again is a special reaction. You can't just use, aqueous acid, won't work. You've got to use sulfuric acid in water, and you've got to throw in mercuric sulfate, mercury 2 sulfate, right? And why? It's because the reaction with a triple bond is just so damn sluggish that you form that vinylic carbocation, which is unstable, and so the mercury avoids it prevents the reaction from being too slow. It makes it an effective reaction. Well, let's talk about hydroboration oxidation. This is a reaction that's all near and dear to your hearts as well. We talked about this a million times in chapter 8. We said, okay, if you have an alkene and you treat it with borane, and this is just review, borane THF followed by hydrogen peroxide and sodium hydroxide, right? We did this many, many times. We said you get an anti-Markovnikov addition of water, you make an alcohol like that. Okay, so that's in the alkenes chapter. But now we're talking about hydroboration oxidation of an alkyne. So it says here that hydroboration oxidation, I'm just reading off this slide, it says it's the same as for alkenes. It's regioselective for anti-Markovnikov addition, right? This carbon is the one that's richer in hydrogen. So since it's anti-Markovnikov, it's the one that's going to take the hydroxyl. And this carbon is the one that's going to take the hydrogen. But look what you get. You get another enol. But this enol doesn't tautomerize to give you a ketone. This one is going to undergo tautomerization to give you an aldehyde, right? So you end up forming an aldehyde, which is kind of interesting. Okay, but in this case, the tautomerization is not acid catalyzed because we're not in acid. We are in base, okay? So it's going to be base catalyzed. So let's look at the mechanism of base catalyzed tautomerization. This is another mechanism that you need to know. Okay, everybody who's ever studied organic chemistry needs to know the mechanism for the tautomerization of an enol in base or an acid. So the first step is a proton transfer of the proton off the hydroxyl. We have an enolate that's formed. So check this out. Check out an enolate ion. Look, you've got the enol, and then it's an 8, right? Because it's got a negative charge. Think about 8 in chemistry: sulfate, carbonate, nitrate, right? Something with a negative charge. You have this resonance contributor here. You do another proton transfer, and you end up with your aldehyde. Okay. Again, mechanisms are the kind of thing I could sit here and talk about it all day, but until you sit down by yourself with a blank sheet of paper and give it the old college try, it can be difficult to understand what's going on. Well, something I want to float here with you is that if you're treating your alkyne with boron THF, blah, 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 hydrogen peroxide, sodium hydroxide, I shouldn't say blah, blah, blah. But anyhow, you get an enol, but the enol's got a double bond in it. Okay, why wouldn't that do another anti-Markovnikov addition? Okay, why couldn't it just do it again? And the answer is technically it can. Okay, it could keep doing it, and that's not very useful. Okay, because you want to stop at one addition. Now, how do you get it to stop? You know, at one addition? Because you see here, it just keeps going and going and going. You keep adding boron to the molecule. And the way that we avoid that, so when we do the hydroboration oxidation of an alkyne, we usually don't use boron THF. So instead of the first step being BH3 THF, we're going to cross that out. And the first step of hydroboration oxidation with an alkyne, we're going to use a reagent called 9-BBN, or we're going to use something called dicyamyl boron. The structures of both are shown here. Oops, I didn't mean to do that. So 9-BBN is this bicyclic compound here. It's 9-borobicyclic 3,3,1 nonane. I'm not going to ask you to draw that molecule. And dicyamyl boron is this guy here. What do they have in common is what I'm more interested in. And what these two have in common is that they both have a boron-hydrogen bond, but then they both have big, bulky R groups attached, right? This one's got, you know, this whole thing, which is the two R groups. And those bulky groups that are attached to the boron, the bulky alkyl groups, they prevent a second addition. So they basically prevent this from happening. Why? Because they're so sterically hindered, okay? So the first step, we use what we call a hindered boron, which again, could be 9-BBN, structure shown below, dicyamyl boron, and in the MCAT and in the ACS study guide, instead of those, they'll just write R2BH. And I think our book does use that from time to time. All that means is that you have an R group that's big and bulky that prevents, you know, a second addition from occurring like that. All right, so the modifying borate reagent allows for the conversion of that terminal alkyne to the corresponding aldehyde rather. We prevent a second addition, which would just give us a bunch of messy products. I noticed something that I just put in my notes here that is a shorthand for 9-BBN, 9-BBN, which is that big bicyclic structure. Sometimes you'll see this, and you might see it perusing the internet, is they'll write the boron like this, and instead of writing all of this bridged bicyclic structure, what they'll do is they give it a real funny shorthand, which is this. They make a ring like this, and then they put another thing like this, which indicates that there's a bicyclic system. Anyhow, it's just a shorthand, right? Chemists come up with all kinds of shorthands for stuff. Anyhow, there we go. So let's summarize. What did we learn? If you have a terminal alkyne, you can do a Markovnikov addition of water across that using mercuric sulfate with sulfuric acid and water. That'll give you a methyl ketone. And we talked about anti-Markovnikov addition, where you use the hindered boron, which again, this could be 9-BBN. It could be dicyamyl boron, either way. But again, I just showed you that we just put R2BH and that works. I'm going to be honest with you, most of my students just love 9-BBN. I don't know if it's easy to remember or what. They seem to gravitate towards that. If I ask them in class out loud, they'll say 9-BBN, you know, Mr. Dan, you got to use 9-BBN, okay? There we go. So something else I should include here is that this should actually say, when it's a terminal alkyne, you end up with a methyl ketone, okay? Like that. All right, that's a terminal. If it's internal, you don't necessarily end up with a methyl ketone. So let's take a look at a problem here. The first one, we're taking a triple bond. We're making a methyl ketone. So what does this mean? This means it's going to be the Markovnikov addition of water. So we're going to treat the starting material with sulfuric acid in water and mercury 2 sulfate. And let's draw the structure of the enol that's produced. So remember, this is the carbon with the hydrogen, so it's going to get richer in hydrogens. And the other one is going to take on the hydroxyl. We have our cyclohexyl group up here, like that. So this is the enol that is going to tautomerize to give you the methyl ketone. All right, and the next one, you're making an aldehyde. So again, this is a anti-Markovnikov addition. So the first step is to use the hindered borane. Let's choose 9-BBN. And the second step is the exact same as the anti-Markovnikov addition of water across a double bond. So hydrogen peroxide and sodium hydroxide. That's going to give us this enol. So let me just draw it carefully here. What am I doing? End up with this enol that looks like this. Like that. And that enol is going to undergo tautomerization to give you, I'm missing a carbon here, aren't I? Oops. Fix this. So 1, 2, 3, 4, 2, 3. 1, 2, 1, 2, 3, 4. So 1, 2, 3, 4. Come on, you. There we go. That's better. And that is going to undergo tautomerization to give you the aldehyde. All right. So again, a lot of memorization here in these reagents. And again, here, instead of 9-BBN, you could have also used, you could use R2BH, that will work, or dicyamyl borane, that works too, right? They all work. In the alkenes chapter, we talked about halogenation, how we proceed through a bromonium ion, and then you get anti-addition of the 2 bromines or 2 chlorines, whether it's chlorination or bromination. Well, you can do halogenation on an alkyne as well. If you treat it with excess of the halogen, whether it's chlorine or bromine, in a solvent like carbon tetrachloride, you end up with a tetrahalide. So you add all, you get 4 new halogens attached to the molecule. I can't think of a whole ton of synthetic utility for this reaction, but it is one that you need to know. And if if you're wondering, like, why can't you do fluorination? It's because it's too violent. Okay, too violent. It's just too fast. And if you try to do iodination, it's too slow. So that's just takes up too much time. Well, if you only use one equivalent of a halogen, however, and I like to specify, so you write one equivalent. I like to abbreviate it like that. In that case, you only get the one halogen, molecule added. So you get the 2 halogen atoms added in both syn and anti-addition. Now it says that the mechanism for alkyne halogenation is not fully understood. If it was like the halogenation of an alkene, you'd only get the E product. But we actually end up with a mixture of the E and the Z as well. So that's kind of strange, right? So this is me going back to the mechanism thing. Remember when I switched over to that blank document and I talked to you about vinylic carbocations? Well, here that same kind of thing is rearing its head again in this chapter, right? The mechanism isn't all that well understood, right? If it was well understood, then it would, again, proceed through a bromonium and you'd only get the anti-attack. But here you get a mixture, and so, well, the mechanism can't be, the exact same as that for an alkene. So again, not that well understood, and that's really all you have to know about this, is if you treat an alkyne with excess of chlorine or bromine, you end up with a tetrahalide. And if you treat it with one equivalent, you end up with a mixture of E and Z of only one equivalent of the halogen being added, whether it's chlorine or bromine. So let's move on to ozonolysis. Again, this is a reaction that we talked about in the alkenes chapter. I don't know where there's room to write it, but we talked about the ozonolysis of an alkene. So I'll refresh your memory. That's where we took an alkene and we treated it with ozone in the first step. And then in the second step, we used dimethyl sulfide, DMS, or we could have used zinc and water. That works as well. And in that case, you'd end up with an aldehyde, right? You'd split this down here like that. And I talked with the skill builder. Well, when we do the ozonolysis of an alkyne, there's a couple of differences. The first one is that the second step is different. It's not DMS, okay? So with an alkene, the second step was DMS. It is not DMS. The second step now is that you just use water, okay? And when you have an internal alkyne, you break that triple bond and you end up with 2 carboxylic acids. Okay, so instead of 3 bonds to carbon, okay, all 3 of these bonds are ending up in oxygens, right? 2 of them are going to the oxygen of a carbonyl and the other one's going to the hydroxyl, okay? And then you do the same thing with the other carbon like this, okay? There you go. So there's no skill builder for that, but you just break that in half. The mechanism, I don't even think is discussed at all in our textbook. I know the mechanism was discussed slightly in the alkenes chapter, but in the alkynes chapter, it's not covered at all. Now that's when you have an internal alkyne. If you have a terminal alkyne, which we're going to see a lot of, you produce a carboxylic acid from one side, okay? But the side that has the terminal, the side that has the carbon bound to the hydrogen, that one actually produces carbon dioxide gas. So this is just CO2. Okay, so you actually end up releasing gas in that case. So that's really all our book says about ozonolysis. It doesn't really give you any more information than that. Let's see here. All we have is a couple of questions I don't want to look at. The first one says, predict the products of this reaction. So we have our alkyne. We're going to break it down the middle here. You can see that it's symmetrical, so you're only going to end up with one product in this case. You have the 5-membered ring. There we go. We have a carbon here and a carbon here. So we only have one carbon coming off, right? We had 2 carbons in the the triple bond, but you only have one carbon coming off of the ring in one side and one carbon coming off the ring. So we have a carboxyl group, and we have a second equivalent of this. So we'll just put ×2, and that's it. Give me a thumbs up if you follow me on that one. It's not meant to be a brain buster or anything. It's more just kind of knowing what's going on. Allison, I just saw your comment. It's 100% true. It's 100% true. Chemists love to have more than one way to describe everything. I don't know if it makes them feel good about themselves or what, but I think you're absolutely right. Anyhow, so here it just shows you the product. So the cool thing about this question is that when you have a symmetrical alkyne, you double your yield, right? Think about it. If somebody asked you to make this molecule and you had this as a starting material, well, if you started it with 1 mole of this, then you end up with 2 moles of this. So it's kind of cool when you think about it. Let's see here. It says, draw the major product that's expected when you treat this alkyne with ozone from the ozone generator, the ozonizer, and then water in the second step. So look, we're going to break the triple bond here. Then I think this one is really just a matter of counting the carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 carbons total. So let's write out 11 carbons in a chain. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And on each of the terminal carbons, on carbons 1 and 11, we're going to have a carboxyl group. And there you have it, my friends. That's it. That's the product. This is called undecane dioic acid. So undecane dioic acid. Anyhow, there you go. So I don't think ozonolysis of an alkyne is all that bad, especially once students figure out the ozonolysis of an alkene. They kind of get the gist of it there. Let's see. Let's talk about one more section, and then maybe we'll take another break. But yeah, let's look at one more thing, which is the alkylation of a terminal alkyne. This is kind of going back to almost back to section 9.3 when we talked about the acidity of acetylene and terminal alkyne. So if you have a terminal alkyne, I mean, we talked about this at length today. We said, okay, sodium amide is a great base for deprotonating. Okay, rip that off and you can make an alkanide. Well, think about that. You've got a negative charge on this carbon. That's going to make a very good nucleophile, right? Okay, so alkanides are really good nucleophiles. I mean, if you put them in the presence of a methyl or a primary alkyl halide, is that going to do an SN2? You bet your bobby socks it will, right? You've got your nucleophilic attack here, followed by a loss of leaving group like that. And look what we've done. We've made a new carbon-carbon bond. if you remember earlier on in this class, I've told you, and I probably repeated myself, that if you can find a way to make a carbon-carbon bond, you will find a way to be famous in organic chemistry. People will like you. Anyhow, so if you think about it, I mean, and I'm sure these aren't the kind of things that you ponder as a student trying to learn the subject, but let me just tell you at face value, we don't know, we don't have many ways to make carbon-carbon bonds, okay? There's not a lot of ways to do it. So whenever you find a way to make a carbon-carbon bond, you learn it. You learn it well, okay? You learn how to do it in the lab. You learn how to draw it on paper. You learn all the nuances because they're so useful. So what we can do is we can do the alkylation of a terminal alkyne. We can just take that terminal alkyne, we can deprotonate it in the first step. So we would take our sodium amide, we would rip off this proton, we would end up with the alkanide. So let me draw the alkanide that you would end up with, which again is a TATSI nucleophile. So it's going to do an SN2 reaction on your ethyl iodide, which is drawn here. Look, nucleophilic attack, loss of leaving group, and wow, a new carbon-carbon bond was formed. What's even neater is if you start with acetylene, you can do it twice. Why? Because acetylene has 2 carbon-hydrogen bonds. So what you do is it's a series of 4 reactions, but you make 2 carbon-carbon bonds in the process. So what you would do is you would first treat it with excess, or sorry, not excess. You would just treat it with sodium amide, followed by your alkyl halide. You're going to add 1 alkyl group, and you do the same thing all over again, and you add a second alkyl group, just like that. Okay. Now, one thing I want to point out to you here is that the order in which you add those 2 R groups is not important. So I'll put order is not important. So you could add, let me call one of them, I'll call this one R1, okay? And I'll call the other one R2, so R2, okay? It wouldn't matter if you added R2 first or R1 first, that doesn't matter at all, okay? So very cool. So note that double alkylation has to be done stepwise. Like you've got to do it 1 step at a time. First, you add your sodium amide. You end up producing acetylide, which is this, right? After step 1. Then after step 2, you do the alkylation, right? Which is just your SN2 reaction. Then you would treat it with sodium amide. Again, you would end up with the alkanide this time. So you end up with this, okay? And then after treatment with methyl iodide, you end up putting the methyl. And again, the order, if you added the methyl group first, ethyl group second, it doesn't matter, okay? The important thing is that you made 2 carbon-carbon bonds, which is pretty cool. Always a cool thing in organic chemistry. So let's take a look at a question and see if we can apply this. It says, starting with acetylene, which again is just ethyne, it's the simplest possible alkyne, show reagents that you would use to prepare each of the following compounds. So if we wanted to make 1-butyne, which is this compound, all we're trying to do is add an ethyl group, right, to acetylene. So we would start with acetylene. So I'll just draw it like this. You know, if you want to draw it, you know, explicitly with the carbon hydrogen drawn out, I mean, whatever, it's fine, okay? So what would we do? We'd start with acetylene. We would treat that with sodium amide. I'm going to do it stepwise just because I'm the instructor. If you want to write sodium amide followed by ethyl iodide, that's the answer. Then you end up with the product. Good. There's nothing wrong with that. Since I'm your instructor, I'm going to go into the gory detail. So you make acetylide, which is this. Then you would treat it with ethyl iodide or ethyl bromide, doesn't matter. You do the SN2, and then you would end up with 1-butyne, just like that. So again, first step, sodium amide, not excess. Second step, in this case, would be ethyl iodide or ethyl bromide. Okay, the next one, we want to add a benzyl. Right, remember I told you, or I think I told you, and I'm 99% sure I did, that when you have an aromatic ring with a CH2 attached to it, like this is called a benzyl group. So you've got methyl, ethyl, propyl, this is a benzyl. So we want to add benzyl on one side, and then we want to add ethyl on the other. So let's do it. Let's just write out the steps. So first you would take it and you would treat it with or take acetylene, you'd first treat it with sodium amide. Your first electrophile, let's add the benzyl group first. So for that, we'd use benzyl bromide. So let's draw out the structure of benzyl bromide, which is this. If you want to use benzyl chloride or benzyl iodide, that would work too. We'll put benzyl bromide. That will give you this intermediate, which is this, okay? Then in the next step, you're going to treat it with, and I'm running out of space here. Maybe I write too big, I don't know. And then in the second step, you'll treat it with ethyl iodide. And there you go. That's going to give you your product. Give me a thumbs up if you're following me on alkylation of a terminal alkyne. If you're like, yeah, I can hitch my wagon to that. It's not too bad. Sodium amide is a great base, powerful base, very strong base, can effectively deprotonate a terminal alkyne or acetylene, okay? And that, my friends, covers all the new reactions in chapter 9. They're done, okay? If you go to the next section, it's the synthesis strategies. And at the end, it covers all the reactions that we learned in this chapter. So there's a bunch of reactions in here, but remember, we've looked at many of these in the alkenes chapter. We looked at variations of them. So let's go over them quickly. If you take a geminal or a vicinal dihalide, you treat it with excess sodium amide followed by treatment with water. That's a great way to make an alkyne, a terminal alkyne. If you treat that with excess HX, so HBr or HCl, you're going to make a geminal dihalide. And again, that's the one that's the termolecular mechanism. So termolecular mechanism. So I'll never ask you to draw it, but you should know that it's a termolecular mechanism. Let's go clockwise. So we've got the next one is adding one equivalent to do a hydrohalogenation, which is Markovnikov addition. The next one is a Markovnikov hydration, but you've got to use mercuric sulfate to spruce it up. You make an enol that tautomerizes to give you a methyl ketone. Next, we're doing anti-Markovnikov addition. So this one is Markovnikov addition. This one is anti-Markovnikov, but you can't just use borine and THF. You've got to use a hindered borine, which you can just use R2BH to describe. Second step is the same as the hydroboration oxidation of an alkene, so hydrogen peroxide and sodium hydroxide. Again, that gives you an enol, but it tautomerizes to give you an aldehyde. Next, we looked at one equivalent of a halogen being added to give you this alkene. Then we said if you use excess, and again, this one here, we said you get a mixture of E and Z. The next one is treating it with excess. You end up with a tetrahalide. I can't think of a ton of synthetic utility of that, but whatever. The next one is an ozonolysis. Notice that the second step is using water, not DMS. That's for an alkene. For an alkyne, use water. And if you have a terminal alkyne like we do here, you end up with carbon dioxide instead of 2 carboxylic acids. Next, we have alkylation. So we do the deprotonation. This is what we just covered in the past 5 minutes, followed by alkylation. And then we saw that you can reduce that to a transalkene using sodium metal reduction. We saw that you can reduce it completely just using plain old hydrogenation. And then we saw that you could use Lindlar's catalyst, which is the poison catalyst, to do a syn addition of hydrogens to give you a cis alkene. And that covers all of the new chemistry that we learned in this chapter. That covers the whole kit and caboodle, so to speak.